use, we'll use the EasyCrypt proof assistant to specify the syntax and security for a cryptographic algorithm, and also to specify the algorithms themselves and the assumptions, right? So we'll have specifications of what it means for something to be a block cipher, for example, or a PRF, what it means for something to be a secure PRF, so security models, security experiments, and all those things, and then the assumptions. So I just mentioned secure PRF, but also the security goals. So what it means for something to be a secure block cipher, for example, or a secure encryption scheme, non-spaced encryption scheme in this model, in this case. So and then also specifying the algorithms themselves concretely in the language, and then also develop the proofs of correctness and security in EasyCrypt itself. So we have several languages that will be juggling to do all those things. In the second part, what Benjamin and Vincent will talk to you about is the Jasmine language and compiler, which is designed to write high-speed crypto code and compile it down to assembly. It also automatically checks that the Jasmine programs are safe, in the sense that they don't address memory that's not been defined or that's out of bounds, and that they're using registers correctly. But they also, the compiler is equipped with a proof that the high-speed assembly code that's produced is equivalent to the Jasmine program that was input in the first place. And the tool also provides us with the ability to extract Jasmine code to EasyCrypt to do correctness and security proof. So we can take the Jasmine implementation, extract to EasyCrypt, and then prove that that extracted code is actually equivalent to something we've done a security proof on. So we can carry the security proof over to the Jasmine code in that way, and separately extract to EasyCrypt to get a proof goal that's to prove that there's no side channel leakage, in this case only for constant time, and again proving that in EasyCrypt that the Jasmine code doesn't leak through the timing side channel and cache timing as well. And so separately proving the algorithmic or the high-level security of the code and side channel security. So as I mentioned, we'll be discussing all of that through a relatively simple example, and I'll go through it very quickly on the slides, and then we'll dive quite quickly into EasyCrypt as well. So the example we'll be looking at is, as I said, a simple encryption, simple symmetric encryption, non-spaced from a PRF or a PRP. So a pseudorandom function or pseudorandom permutation. We'll be talking mostly about the pseudorandom function model, because doing the proof for the PRP is slightly more involved, and that could be an exercise for those of you who finished the easy exercise in the first place. We'll be keeping it very simple by saying we want to encrypt a plain text whose size is exactly the same size as the PRF output. So we're not going to try and encrypt multiple blocks of plain text, although one of the exercises, again, is to try and do that proof for a message or a plain text that fits in 2 blocks of the block cipher or the PRF. And then ultimately, you might want to do it for arbitrary messages with padding and all of that, but we're not going to even try that in an hour and a half. So the construction is as displayed here. So you've got the pseudorandom function, which is keyed, and that key is fixed and sampled in advance. And the input to that PRF is the nonce, and the output is going to be used as a mask that's XORed onto the plain text to produce the ciphertext. So we've really got a simple construction that's going to look very similar to modern stream cipher constructions that you may have encountered. And what we want to prove about this construction is that it is a secure non-spaced encryption scheme for a particular setup. So in terms of provable security, and again, this is at algorithmic level, we'll keep things very abstract. So we're not going to talk about bit strings right away. We're just going to say, well, we've got a key space, which we'll call K, and a non-space, which we'll call N, and a message space, which we'll call M. And then we'll assume that the ciphertext space C is equal to the message space M. So that PRF or PRP is actually a function from the message space to itself. Sorry, that's not correct. It's a function from nonces to messages that's indexed by the key space. For key generation, we'll be, again, keeping it simple. We'll sample the keys uniformly at random from the set K. And encryption will be done as specified above, except now I'm writing it in pseudocode, or actually in code, where when we want to encrypt under K with nonce N, when we want to encrypt a message or a plaintext M under key K with a nonce N, we're going to just compute the function f, the pseudorandom function f, indexed by K with N as input. That's going to give us a mask that we're XORing on the message. So again, this is just programmatic description of exactly this construction here. And for the decryption, we're just going to do the opposite, right? So we recompute the mask from the key and the nonce, and then we XOR that onto the ciphertext, and that should give us the message back. And we'll be proving that this is correct. I'm going to not do this proof on paper, but we'll be proving it formally as well. And you'll see that that proof is actually quite simple. So again, we're keeping things very abstract. We've got abstract spaces for the key space, the non-space, and the message space, message and ciphertext space, and then some abstract function f that has the given type. So it's a function from keys and nonces to messages, and then a couple of algorithms that we define concretely, right? The key generation is defined concretely as sampling uniformly at random, and the encryption and decryption algorithms are specified concretely from the abstract function f. What we want to prove about that specific construction is that it's a secure non-spaced encryption scheme. And by security here, we mean the notion that you might see referred to as in $CPA, so in random CPA, which is indistinguishability from random ciphertexts under chosen plaintext attacks. So what we mean here is that we'll say that that a scheme is secure, has that notion of security, if no adversary A can distinguish between these two experiments. So the one that's on the left is allowing the adversary to interact through that oracle that we give, relink that we give to the adversary, with the real encryption scheme, so this enc construction that we just described, with a key K that's fixed in advance, right? So the experiment samples the key K uniformly at random. That's what this double arrow here means. It's going to sample small k uniformly at random from the key space K, and then let the adversary run and allow them to interact with the real enc oracle that computes encryption under that key K. The adversary eventually gives us a bit B, which is the result of the experiment. On the other side, in the ideal experiment, we won't sample the key K in advance. We just let the adversary run with oracle access to an ideal encryption oracle. And the ideal encryption oracle, instead of computing the PRF, is going to simply sample the ciphertext C uniformly at random from the set of ciphertexts and return that. And same thing, the adversary eventually gives us a bit B as an output, and that's the result of the experiment. And the whole idea is that we'll be saying that, well, essentially this on the right in the ideal game, that's the ideal functionality for encryption, and that's producing ciphertexts that don't even depend on the plaintext. So they're perfectly hiding in the sense that they contain absolutely no information about the plaintext. And we'll say that the scheme enc here, this encryption scheme is secure if no adversary can distinguish between these two worlds. And by distinguishing, we mean can produce a different output with significant probability. So here, down there, it's a more traditional version of what I just said, where you define an advantage, which is the distance between the distribution of true in the left experiment, of the adversary returning true in the left experiment, and the distribution where the adversary returns true on the right experiment. So we're really talking about the distance between the two outputs of those experiments. And again, we'll be quickly diving into how to express that into EasyCrypt. But immediately, one could already see that there are usually, when you see that definition on paper, you will also see restrictions, right? Already you can see, well, if I'm the adversary, I've got a quick strategy to win this game, right? To distinguish between these two worlds. I can just feed the same nonsense message to my oracle twice, and get two different outputs in the ideal world and the same outputs in the real world, and therefore distinguish. And so in practice, when you see those definitions on paper, you'll see restrictions that are applied where the adversary cannot make repeat queries. And so in this case, what we want is security against nonce-respecting adversaries that don't repeat nonces in their queries to the oracles. And in general, you will see that as a side condition that's placed on adversaries on paper. In EasyCrypt, those restrictions have to be made explicit. So I kind of jumped ahead of myself there. But we'll see in those definitions that the checks that we're not repeating nonces will appear, and additional checks on the number of queries will appear explicitly. So that's the security goal we have on those on that encryption algorithm. The assumption we'll make again is that the function f is a pseudorandom function, and those are usually specified as a family of functions that are indexed by the key. And here, this is again how we'll specify it. So we'll have a function of type f that takes the first argument, which is the key, the second argument, which is the nonce, and gives us a message. And so we'll really see this as a family of functions from nonces to messages, where the key is used as an index to select which member of the family we're actually using. And we'll say that small f is pseudorandom if it can't be distinguished from a truly random function. So in EasyCrypt, and here on that slide, the truly random function on the ideal side, we're actually lazily sampling it. So we're not going to sample the function uniformly at random in the whole space of functions. We could do that, but instead what we do is just say, if the adversary queries this truly random function on an input that we haven't seen before, we'll just sample the output uniformly at random and store it for later use and return that to the adversary as well. So we're going to lazily sample that that random function. This is equivalent when when everything is well behaved and finite. This is equivalent to a setting where you would sample the function in the function space. And same thing again, we express the fact that f is pseudorandom as the difference, as the distance between the probability that the adversary returns true on the left and the probability that the adversary returns true on the right. So again, the adversary wins if he can introduce a difference in behavior between the world where he interacts with the real pseudorandom function and the world where he interacts with a truly random function. So what we will prove is that we can always we can build an adversary B or a reduction B. So we'll construct that reduction B that is going to be such that the advantage, so the CPA advantage of the original adversary A. So for any A, we're going to build that adversary B such that the insecurity of the encryption scheme against A is going to be equal to the insecurity of the PRF that we're using as the building block for our encryption scheme against B. So we're really building a reduction that says, well, whatever adversary you can show me against the encryption scheme, we're going to be building an adversary against the building block that wins with exactly the same probability, right? So its advantage is exactly the same. And again, here we'll actually need some restrictions on the class of adversaries we consider, and there are some that appear explicitly in EasyCrypt, and some that don't appear explicitly in EasyCrypt compared to what you might see on paper. So those that do appear explicitly in EasyCrypt is that we have a nonce-respecting adversary. So the proof we're doing only applies to adversaries that do not repeat nonces in their queries. And it only applies when the adversary that we consider, the adversary A that we start from, places at most Q oracle queries, where Q is going to be some bound that should be less than the size of the nonce space, essentially, because otherwise the adversary necessarily repeats a nonce. So if we don't place those restrictions, we'll always be able to find and exhibit an attacker that has a large advantage that won't be bounded. And then we've also got some restrictions that you would find on paper that we won't have in EasyCrypt at all. And those are because the proof that we're doing is it's an exact security proof. So we're really saying all we're proving is that these advantages are equal, but we're not considering the asymptotic security or the implication on security itself. We're just saying these advantages are equal. Here is the reduction B, and you can consider its complexity and the fact that it's actually a realistic adversary against the PRF separately, but we're not going to come up with that argument. And so the kind of additional assumptions you need to make in order to get a high-level security result, a security proof, is going to be that the attacker, the indel SCPA adversary A, executes in at most T steps, and that the PRF cannot be broken, cannot be distinguished from the truly random function if the adversary only has roughly 10 computational steps at its disposal. And again, we don't need those assumptions to prove the bit of the proof that we do in EasyCrypt, but you will need them if you want to conclude with a security claim that is asymptotic or holds for a particular class of adversaries that are bounded in complexity. So again, some of those restrictions will appear explicitly in EasyCrypt, and we will need to manage them properly. So let's look quickly at the EasyCrypt formalization. So I'll try something, and hopefully that will work. So let's look very briefly at what is going to happen here. So this is EasyCrypt on the right. Well, it's an Emacs buffer that has EasyCrypt running in it. I should be able to know that's zoomed in instead of zooming out. Let me zoom out so we can see everything that's going on. And I'll try to keep things moving on the right at a reasonable rate, or in a reasonable size without losing too much of my width. So what we start with is a bunch of imports, and that's going to always be the case in most EasyCrypt proofs that you look at, or most EasyCrypt files. You'll have a bunch of imports at the start that, and there are several classes of them. So here we have on the first line, these things are libraries for data types and distributions that we actually use in the specification, or that we might end up using in the proof as well. So here we've got something about core data types. So that's going to be integers, real numbers, booleans. All of those are in the old core library, and just importing them is going to be useful just because everything we do involves integers, booleans, and real numbers. SMT maps. SMT maps, sorry, that's a library that talks about maps, so functional maps, which are going to be partial functions from a domain to a codomain. And we'll be able to specify what happens when we update those partial functions in a particular point, when we add additional points into the partial function, so when we extend the domain, and we can define those functions, and we will define those functions little by little. And essentially, when we talked about this this lazily sampled function here, this T of X is essentially is going to be implemented as one of those maps. So you can see it as literally a mapping that we're building element by element or input by input. We'll also be talking about lists, just so that we can keep track of the nonces that have already been used, for example. And we'll talk about distributions because we talk about distributions all the time, and we need to sample uniformly those keys and those outputs in the truly random function as well. Then we'll do a couple of things. So the first thing we'll do is clone this nbyank. And so what this clone does, we'll see in a minute. So nbyank is defined in another file. And I think Benjamin and Vincent, if you could actually post the link, if you haven't done it already, the link to the files in the chat, that would be excellent. So all the files that we're talking about will be in there, and you can also retrieve the exercises when the time comes. So so let's open this file nbyank, which is again another file in the same development, and that file actually defines what it means to be a non-spaced encryption scheme. So this definition that we had here is going to be something that we have separately in a different file that we define for all possible key spaces, non-spaces, plain text, and ciphertext. So here we've got a similar prelude where we've got all core, so bool, real, and integers, and then we import the library that talks about distributions and the library of lists, because we need to talk about repeat nonces and repeat queries, essentially. And then we just declare that we've got a type for keys, a type for nonces, a type for plain texts, and a type for ciphertexts. The fact that we just declare them means that, so essentially a type in EasyCrypt is a set that's not empty. So we just say there exists some non-empty set of keys, some non-empty set of nonces, and same thing for plain text and ciphertexts. And everything we're doing below is going to apply to all of those, as long as they meet certain
Yeah, I think Francois. So we have to wait for Francois to rejoin.
Yeah, that's the wonder of online meetings, right? So Francois is trying to reconnect. He asked me to put some hold music on. I don't have hold music, and I don't know how to stream it, even if I had it on Zoom, but he should be there any second.
Yep.
At least Skype works again for him. So Francois is trying to get a network connection. Seemingly, there are some issues with the university network on his side. I am not sure where the file actually is. I think it's... Maybe one of the others can point us to the EasyCrypt file, then people can at least have a look at the EasyCrypt file during that time.
I will need someone to allow me to share my screen again. Apologies for dropping out unexpectedly.
Your co-host, you should
Excellent.
be able to share again.
Yeah, I should be able to, and I can. Excellent, cool. I don't know where I dropped out. So Andreas, if you can tell me what I was saying.
You were explaining the imports.
The imports.
You came to the list. I think this was the last thing.
So that was almost irrelevant. So we've got a bunch of imports, and then we've got a set, like a bunch of types that we introduce that essentially frame the entire development. So here, anything that we define, that we declare without defining it, is going to be universally quantified. So we're proving like everything that follows is defined for all type of keys, for all type of nonces, for all type of plaintext, and for all type of ciphertexts, and for all distributions over ciphertext as well. And again, what follows is mostly definitions. There is a proof at the end. I won't talk about it that much yet, but most of the things we define here are just definitions. So there's no need to restrict things much. We're just saying all those definitions that can be parameterized by keys, nonces, and plaintexts. And here, so we've got also, again, explicitly the number of queries that we can make to the encryption oracle, and then an operator that checks if a nonce has already been used or not. And it's just defined as an abstract operation here from nonces. Given a nonce and a nonce list will tell us whether that nonce appears in a nonce list or not. Intuitively, we can make more complicated setups, and in fact, this definition is instantiated in a more complex way when in the exercise proof where we extend it to 2 blocks. So you'll see that. We've also got a need for a default ciphertext, and I'm not sure if that was cut already or not, but as I mentioned, or not, a type in EasyCrypt is a non-empty set. So we know if we have a type, that's a set that has at least 1 value in it. And so this doesn't place a nasty restrictions on the type. Is just a natural condition that already arises from the fact that the set of ciphertexts is actually an EasyCrypt type. And so that's just, it's non-empty. And we have one particular ciphertext that we call DFLT for default, and that will be used in some settings to return a default value. And given all those types and actually just the types at this stage, we can define what it means for something to be a non-spaced encryption scheme. And so if we go back to what it means for something to be a non-spaced encryption scheme, something that's got a key space, a non-space, and message space, and a ciphertext space, and we've got that here, and that has a keygen algorithm that produces keys, and an encryption algorithm that, given a key, a nonce, and a plaintext, produces ciphertext, and a decryption algorithm that, given a key, a nonce, and a ciphertext, produces a plaintext. So again, so now we've got a new construction, which is this module type, where we give a name to that module type, and that's saying, well, any module, any set of procedures that somebody can provide that has at least these 3 defined with the appropriate types is going to be something that we can put into a box that has a scheme T label on it, right? So we define what it means for some set of algorithm to be considered a non-space encryption scheme. And for any such set of algorithms, we can define what it means for this set of algorithms to be correct. So here we can define a correctness experiment that's parameterized by a scheme. And then we can say, well, given a concrete scheme, like the one that's defined on the left here, we can apply correctness to it and start talking about the correctness of the scheme. And so here, what we mean by correctness, and that's cryptographic correctness, and that's the first thing we'll be proving, is going to be that for all key nonce plaintext, if you encrypt and then decrypt, you recover the original plaintext, right? So we can specify this algorithm in this way. So here, a bit of syntax. We've got procedures inside modules. I'm not sure if that, yeah, I can make it a bit larger. Then we can declare variables. That's just saying we've got some variables that are floating around locally to main. They are not accessible outside of main. We'll also see that some modules can have, well, modules can have global variables, but we don't make use of them in the correctness experiment. And then we can, we have a variety of things we can, of constructions we can use to define those procedures. And essentially, we've got a small imperative language that we'll see more examples of. But here, what we're illustrating is that we've got a construction that allows us to call other procedures. So here, this line is saying the variable C contains the result of calling the scheme.enc on values k, on input k and np, right? So scheme.enc is going to be the encryption, the enc procedure that's provided by whatever concrete module of type scheme T is passed as input to the correctness experiment. So when we parameterize a module with another module, we can then access or use the procedures that we know are provided because of the type that's given. So here we've got this module type scheme T that tells us anything that EasyCrypt will let us put in this box, in this as an argument to this correctness algorithm, will necessarily provide us with these 3 oracles, and so we can use them like this, scheme.enc or scheme.dec. So that's correctness, which we hadn't talked about. What we had talked about and what we have on this slide here is security. And so here we can use similar constructions to define what it means to be an encryption oracle, and what it means for something to be an adversary, and what it means for something to be secure as well. So here we first define what it means to be a CPA oracle, and a CPA oracle is or a set of CPA oracle is any module that provides one algorithm, which we call enc, and that enc, like the one for the encryption scheme, it's not parameterized by the key, right? So here, this relenc and this ideal enc, they take only 2 arguments because the key is kind of built in. It's sampled and built in by the adversary, by the experiment. So the oracle we provide to the adversary only takes 2 arguments, the nonce and the plaintext. And that produces a ciphertext. So that's how we define what it means to be a CPA oracle. And then we can allow the main game to initialize some oracles. And this is useful if, so for example, the ideal oracle in the intermediate experiment, which we haven't seen, actually has some internal state that we need to initialize to the empty in order to make sense of the proof. And so here we just extend it. So we say, well, we've got a procedure called init that doesn't return anything. It doesn't take any arguments or return anything. So it literally just initializes the state to some initial value. And then it also includes all of the oracles that are defined in this module type here. So we'll also have an enc oracle with this type given here. So that's what this include does. Given this set of oracles, we can then define what it means to be a CPA adversary. So a CPA adversary, here we defined it in a way, in an informal way, by saying, well, it's an algorithm that takes no inputs. It takes no inputs. We run it with an empty set of inputs, but it has oracle access to a CPA oracle. And so here that's relenc, here that's ideal link. But what we really mean is that it's really just any oracle that can fit here, we can then run this adversary with access to these oracles. So we use this mechanism where we can parameterize a module with another module, or actually several other modules, to say an adversary is something, so a set of algorithms, or in this case, just a single algorithm that is parameterized by a CPA oracle. So we give access to a CPA oracle to this adversary, and we ask it that given no inputs, so again, given no inputs, it should produce a Boolean as output. And that's going to be this Boolean that we're producing. And this main procedure here, this main algorithm, which is the actual adversary algorithm, is going to be able to use all of the oracles provided by O. So in this case, just the enc procedure that O provides. So we'll be able to call it in the same way that in the correctness experiment, we were able to call the encryption and decryption oracle provided by the scheme. So that's essentially defining CPA adversaries here just by saying a CPA adversary is any algorithm that has oracle access to a CPA oracle produces a Boolean. And once we've defined what it means to be an adversary, we can define these experiments, right? So we've got this $CPA real experiment, which is parameterized by an adversary. So we can do this further below, where we can say, well, we've got the CPA experiment, which is parameterized by an adversary and also by a set of oracles. And we'll just allow the adversary to run with a version of the oracles that's wrapped just to keep track of the nonces that have been used already. So let me just go back through that. So we've got this CPA experiment that's parameterized by an adversary and a set of oracles. And all it does is initialize the oracle and then run the adversary with this oracle and returns its output. Now this oracle set that we give is actually wrapped a tiny bit. So let's look at what that does. And here again, we're layering parameterization. The reason we're doing that is it makes the definition slightly more manageable to look at. So we can define the scheme and then define how we wrap that scheme into a set of oracles. And that's the bit that I skipped over. And then we can define how we wrap those oracles into a layer that lets us keep track of or enforce adversary restrictions. And so here, this WO is literally just enforcing adversary restrictions by saying, so initially we just initialize the oracle state by itself. And then we also have a variable nonces, which is a list of nonces in which we're going to keep track of all the nonces that have been used so far. And we initialize it to be the empty list right here. And then we're going to say, well, the enc oracle that the oracle actually provides, the CPA oracle actually provides, will be making sure that if it's called with the same nonce a second time, or it's called too many times, so more than q times, then we won't answer the query we're given, we'll just return a default value, which is where that default value comes from. So here, again, interpreting that the code here that we're writing, we're saying, well, C is going to be the value we return at the end, and we initialize it to be the default value. Now, if the nonce n that's given as input is not already used in the nonces list, and the nonces list still contains less than q elements, where q is the bound we've placed on the number of queries we allow the adversary to make, then we'll just call the encryption oracle on the inputs that the adversary gave us to produce a ciphertext, return that, but also store the nonce in the list of nonces that we've used. So we'll just be able to wrap any oracle in a layer that allows us to enforce the restrictions we place on the adversary. And this is the place where those explicit restrictions actually come up. Now, given a scheme, how do we build one of those oracles in the first place? Well, this is what these layers here are doing, where we've got a notion of a CPA scheme where we just say, well, we don't care about the decryption oracle, but let's ignore that. But we can provide wrappers that say, well, given a scheme, let's produce the real world oracle that surrounds it, or that's meant to be provided. And all it does is have a global variable that's going to be shared between all of the algorithms that are implemented inside this module. And then the init oracle is just going to generate a key using the key generator from the scheme and store it into that global variable. And then the encryption oracle, which again is not parameterized by a key, that's the one that we expose to the adversary. That encryption oracle just passes its input NP, so nonce and plaintext that it takes as input, down to the actual encryption scheme with the key K fixed to be the one we generated earlier. Right, so we generate the key at the beginning of the experiment, just like we do here, and then the real oracle simply uses the concrete encryption algorithm with that fixed key to produce its output. On the other side, the ideal scheme simply doesn't initialize anything and simply returns a random ciphertext as output, where here this notation is saying that C is sampled in the distribution D ciphertext. So here we don't even specify that the distribution is uniform or anything. If you've got a value in EasyCrypt that has a distribution type, then you can use it in one of those statements with an arrow with a dollar on it, and that's just saying sample in that distribution, sample the value of the left-hand side in the distribution that's specified on the right-hand side. And this actually allows us to do quite a few things where we don't have uniformity, and we can specify almost arbitrary distributions and then sample in them as well. So this gives you a very quick idea of how we formalize this kind of definitions and write them generically to talk about, well, to just define them and tell the tool about what they are. And it gives you a bit of an idea also of how to write those restrictions that are usually not built into the code definitions on paper, and turn them into code that EasyCrypt can actually look at and understand, and that we can reason about in the proof as well. And this idea of layering the restrictions on top of definitions is useful for several reasons. One, it makes the definitions slightly easier to read in general. And the second thing is that there's quite a few proofs that will go through without those restrictions in place, and then you can swap them in and out. Although I don't think this proof actually makes use of this. So now we've got this set of definitions that's given generically for any type of keys, any type of nonces, any type of plaintext. But what we really wanted was to specify them for very specific, one very specific scenario where the ciphertext space C was actually equal to M. And later on, we'll even want to refine that further to talk about bit strings and fixed length bit strings and all of that. And we also want a very specific use nonce function, which is the one that we had down here, that we don't place two queries with the same nonce n. So you might even consider, like, there's reasons why you might want to do something more general. You could have a few times security notion, but here we really want to say if the same nonce is reused, we'll put our hands up in the air and say, yeah, I don't want to give you any security in that case. And so what we can do is use this clone with instantiation. So when we clone nbenc, what we're doing is we're making a copy of the entire file we just looked at and all of its definitions, and just creating a local copy of it with a new name. Except in this case, we're not giving it a name, we're just inlining it into the current file. And as we do this copy, we can actually instantiate some of the parameters that are left abstract. So we had a type ciphertext, and we can actually specify that we want it to be equal to the type of plaintexts that's defined in nbenc. And same thing for the use nonce operator that's left completely abstract in this abstract definition that we just looked at. We can actually give it a definition. So here, the use nonce operation, we can say it is the function that to some nonce n and some list of nonces returns true if and only if n appears in the list nonces. So this is a lambda expression. Another way of writing it for those of you who are less familiar with lambdas could be like this, where we say use nonce returns true on input n in nonces if and only if n is in the nonces. And obviously that doesn't work anymore, so I'll just revert that definition, that change. I think it's just that I need this. Actually, I know what it is, so I'll just undo this. So we can specify. So here we're literally just saying, please give me a copy of this nbyank file with these specific values for the type ciphertext and for the operators use nonce. So one of the so all of that will appear. So here we can make a print. So we could print the entire. No, we can't print the entire theory, but we can print the CPA game itself, where you can there's actually no difference here, but we do now have a copy of the CPA game. One thing we can do is print WO, which was that wrapper that was enforcing the security definitions. And we can see that actually we can't see anything again because we've got, we did this in a particular way. Okay, so that's fine. But you can see that those definitions now appear in our current context. And we can actually now print what I wanted to illustrate. The type of ciphertext, the type ciphertext that existed, it's now defined to be equal to the type plaintext. So we've just pulled in all of the definitions we were looking at earlier, the abstract definitions, and made them slightly more concrete here by just enforcing these two constraints. So we really want essentially pseudorandom functions where the encryption schemes where the set of plaintext and ciphertext is the same, and we want a nonce-respecting. We want to consider nonce-respecting adversaries. Now we've got the same kind of idea. We can define generally what a PRF is, and again we've got the same idea of a file of a theory, PRFTH, where we have a bunch of abstract definitions for any type of inputs and outputs, where input is going to be just the input to the function and the output, and then we've got a notion of keys as well, and so let's bypass entirely and just say, okay, so we can do the same thing and have a clone of that PRF theory that defines abstractly what the real and ideal PRF should be on some type of keys, inputs and outputs. And we actually specify in this case that the type of keys is actually the same type as the keys that came from this definition here, from the nbyank definition. So we'll use the keys from the PRF as keys to the non-space encryption scheme, but that the input to the PRF is going to be the nonces from this non-space encryption scheme, and the output is going to be the ciphertexts from this non-space encryption scheme. And for the output sampling, we're going to provide, again, this ciphertext distribution that's coming from this non-space encryption scheme. So we're really linking those two definitions and specifying that they're working on the same sets, using the same distributions, and using the same constraints on the number of queries the adversary is allowed to make. Are there questions about this? I'm skipping over this because I wasted a bunch of time trying to reconnect, but it is important that we understand what appears from that. So let me just print that. If there are any questions, I don't think I can very easily see the chat at the same time. So Benjamin or Vincent, you can let me know if anything pops up. So quickly, we've got what comes out from this clone. We've got now a function f that's left abstract. So some abstract function f from keys and nonces to ciphertexts. And then we've also got this random function that's specified, which is literally this random function here with the initialization to empty. So we've got this module, again, which is a set of procedures of algorithms that share some global variables. So that global variable here is one of those finite maps that I talked about, which take some, which model essentially functions or maps from nonces to ciphertext in this case. And we're going to initialize it to the empty map that's going to be defined nowhere. And then as the adversary makes new queries, we can specify that if that query is new, we're going to sample fresh and doesn't appear yet and is not defined yet in the map. We're going to sample that, that output at random and store it for future use and then return that. So there's a couple of tricks here. Here we sample outside of the if because it makes proving easier. It makes reading a bit more complicated, but it does simplify proofs greatly, and it doesn't change anything, right? In the case where the input the adversary gives us is already in the map, we sample value and throw it away, so it doesn't change anything. And here we've got a quick notation, a bit of notation. The lookup in a map can actually return a value if the map is defined in that point, in the input point we're looking up at, we're doing the lookup at. But it could also return an error or distinguish symbol none if the map is not defined in that point. And this OGET is projecting that away. So it's saying, well, if it's defined, give me the value, the output value. If it's not defined, just give me a default value. But in this case, we actually know that will always be defined because if it was not defined before, it's defined after running this, this line of code here. So we've got a well-defined function. Right. Cool. Now we're going to place axioms on the distributions we have floating around. So we'll have some axioms that talk about the well-formedness of the distribution, and in this case they're actually specifying it completely. So we first assume that the distribution is lossless, and that's a weird technical detail in EasyCrypt where our definitions, our distributions can be such that the total probability of the distribution is not equal to 1, but is less than 1. And we have to do that in order to capture non-termination because we want to capture non-termination as a phenomenon that reduces the probability of the total probability of a distribution. So we assume that the distribution on ciphertext that we use will always give us a value and will never just loop infinitely trying to give us a value. We also assume that the distribution on ciphertext that we have is uniform. And here what that means is any two values have the same probability. Any two values that are in the support of the distribution have the same probability. And we assume that it's full, by which we mean that all ciphertexts in the set of ciphertexts have a non-zero probability of being sampled when we sample inside the ciphertext. So essentially what we're specifying here with these three axioms is that the ciphertext is the uniform distribution over the type of ciphertexts. So this is a slightly weird way of specifying that. In order to go further and be able to specify the concrete algorithm we wanted, which is recall up here, we actually need slightly more because our concrete algorithm had this XOR operation, this O+ operation that we assumed existed. So at the moment, we have defined this F through the clone of the PRF theory, but we haven't specified what that O+ operator actually is. And so here we're just going to specify it very abstractly. We're going to specify a minimum set of axioms of facts that we need to know about it in order to be able to do the proof. And then later on in the Jasmine part, you'll end up proving that the actual implementation of bitwise XOR of bit strings actually has those properties that are assumed here. So we assume an operator, which we call hat, and is defined to be infix. So these parentheses mean we can actually use the hat operator as an infix operator. And that's an operator over plain text. So it takes two plain texts and produces a plain text as output. So it's really just something that looks like XOR or plus or any binary operations over plain text. And then we assume that that is idempotent on the left. So X or Y, the whole thing XOR Y is going to return X. And that is idempotent on the right first and on the left as well. And so we're really just, again, assuming the very minimum thing we can about it. That any element is its own right inverse and its own left inverse, essentially. And that's literally telling us it's any one-type band essentially that we can use here, but that's expressed in a very abstract way. Given this declaration of an operator called hat, we can then specify the encryption-decryption scheme as written here, just by saying that the encryption of under key k and nonce n of some plaintext p is equal to fkn XOR p. This is actually swapped compared to the definition that's on paper. This is probably accidental because we're not assuming commutativity here. I hesitate to fix that because I think the proof is going to break if I do that. But if we wanted to specify it exactly as we do in the slides, we should probably write it like this instead. So keep that in mind when you're looking at the proof on the slides. There might be some differences due to that in the proof, in the formal proof as well. But we haven't looked at the slides yet. So we've defined encryption, decryption, and then we can already just on this operator level definition, we can start talking about correctness. So we can say as functions and not as stateful algorithms, enc and dec are actually a correct encryption scheme. And we can show that using a lemma, which we can specify here. So here we're giving it a name, which is enc dec correct. And we're parameterizing that lemma with k, n, and p. And this is shorthand for this lemma here, where we say enc dec correct is a lemma that says for all key, nonce, and plaintext, this property holds. The property being that if you encrypt p under k and n, and you decrypt the result under k and n, you get p back out, right? So we're really specifying functional correctness of the encryption scheme as a mathematical lemma. So we're again not talking about algorithms here, talking about mathematical functions. It's a very, very minor distinction. We can do this proof. I'm not going to go through the detail of that, but again, I just lost a bunch of time. I think I'm really running out of time now. So we've got this this lemma which we can prove and move on from, and then specify the actual scheme. And again, what we want when we specify the scheme is specify a set of algorithms that meet this this type scheme T that we had, which was that we've got a key generation algorithm that samples a key uniformly at random in a set of keys, and an encryption algorithm that uses the PRF to generate a mask and then XORs the mask onto the plaintext to produce the ciphertext that we return, and then the decryption works in the same way. So here we've got this small difference between the algorithm, which is describing step by step how the encryption is happening, or the encryption and decryption is happening, from the mathematical specification that was just defining a mathematical function that was doing the same thing. But again, this is a simple example that doesn't really exhibit the differences between it. So we can prove correctness. I won't go through that because I want to go through the more interesting bit, which is proving security.
So François, sorry, I interrupt. There is a question in the chat.
Okay, yep.
Why would the proof break when the operands of the hat operator switch? Because
we don't explicitly assume, so the basic answer is going to be because then the algorithm is using the hat in this direction and not in the other. So we'd have a mismatch between the mathematical specification and the algorithmic specification that we have here. And the reason why we won't be able to prove that they correspond is because we haven't assumed anything about the commutativity of this hat operator, right? This hat operator, morally, we're using it to talk about XOR on bit strings. And later on, we will actually be making it explicit that it is the XOR of a bit strings. But in this particular proof, we're making very minimal assumptions about it, that, that we have this property and that property on it. It's possible that because we've got both directions, the proof won't break, but I don't want to try it live. And that's the reason I mentioned that. So it's possible the proof will work. It's possible it won't. I'm not sure if that answers the question. But the real reason I said it would is because we don't assume explicitly that that operator is commutative. And so that means anything that relies on commutativity we won't be able to prove it. If we needed it for the actual security proof, we would need to assume it as well. Right. Anything else? I take that as a no. And I'll move on to talk about the proof itself, about the security proof itself. Let me just align things back, and I zoomed out, so it's not aligned anymore. It's going to bother me for the rest of the talk. So the security proof, and this is the bit where I am going to need to skip really fast. It's relatively standard in the sense that we're going to be using game hops, and each of those game hops is actually quite simple and on its own. And so the first thing we're going to do is the shape of the proof. We start from the real experiment applied to the concrete encryption scheme that we have. So we've got a fully defined experiment here where we've got the $CP experiment applied to the real encryption oracles, and we'll be modifying it slightly to turn it into, eventually bring it to the point where it's the ideal experiment. And each time we modify it, we'll be bounding the probability that the adversary distinguishes the two different sides of the hop. So here on the left, we've got this $CPA real, where the encryption oracle is the real encryption oracle. And then the first thing we're going to do is say, well, here we've got a PRF. And if we assume that that PRF is secure, then there's no way the adversary will be able to distinguish between the scheme that uses the PRF and the scheme that uses a random function, so the truly random function that we're sampling lazily in order to compute the mask, right? And the way we're going to do that formally is by essentially turning the scheme itself, so this modified enc, is going to become part of an adversary against the PRF. So we're going to take this mXOR bit and push it into the adversary. And now we've got something, a construction that's a distinguisher or an adversary against the PRF itself. And so the A adversary here will be distinguishing these two experiments if and only if the adversary we construct, which is going to be the B or concrete B adversary that I talked about, can distinguish f, small f, so our pseudo-random function, from the actual truly random function that we assume. And again, we'll see that in EasyCrypt if we get to it. But I doubt we will have that time because of technical issues. The second step of the proof is going to say, well, okay, we've got this adversary that works with a modified encryption algorithm. And here, this modified encryption algorithm, we've kind of collapsed the modified encryption algorithm and the lazily sampled random function into a single thing that does the mXOR as well. And we're going to say, well, this distribution here is going to be indistinguishable from the distribution that's produced by simply sampling the ciphertext at random. Why is that? Well, because the nonce-respecting adversary, and again, that's the restriction that we place on A, is never going to be calling modified enc with the same nonce twice. So that means we'll always be going into the branch where we sample T of n uniformly at random, freshly for each of the queries that comes in. And so that means this T of n here is always going to be a fresh random value that's never used anywhere else, or never used anywhere else. And so this enc or some random value that's never used anywhere else is going to be a one-time pad, and that's indistinguishable from just sampling the ciphertext at random. And the proof in EasyCrypt actually shows you how to formalize the argument. So hopefully, and then we can just formalize everything in that way. So we can show that the real experiment is equivalent to the PRF experiment with the real PRF, with some adversary B that we're going to build. And then the second step of the proof tells us that the ideal experiment is equivalent to the ideal CPA experiment is equivalent to the ideal PRF experiment with that same adversary B we've constructed. And that means that the CPA advantage of A is going to be exactly the CPA advantage of B, and B and A have roughly the same efficiency and make the same number of queries, and can come up with those arguments more formally once we see the code for B. So let's look at the code for B. So again, we're doing that proof in the context that we've just described, where we have all those definitions lined up. And now the B adversary, again, the whole idea of it is that we want to take, let me scroll up here. We want to take this adversary A, the scheme, the real encryption scheme that computes M XOR the PRF, or M XOR the result of the random function, and turn it into just an adversary that interacts with an oracle, with the PRF or the random function, right? So we want to abstract away the function f that's used to produce the mask, and just make the scheme compute M XOR that result. And this is exactly what our reduction does, right? So we start from a CPA adversary A, and we actually have a set of oracles O, which is going to be a set of PRF oracles. So let me just print that, because I went quickly over that. But here, oracle, when we clone PRFTH, that came with the definition of this type oracle, which is PRF oracles, right? So the type of oracles that a PRF adversary expects to have access to, that takes a nonce as input and produces some ciphertext. And somehow we need to turn this oracle F that our B adversary has access to into an oracle that the adversary A, which expects a CPA oracle, expects to have access to. So the types are going to be slightly different in the sense that A expects to have access to an oracle that takes a nonce and a plain text as argument. And so that's what this OCPA submodule here is doing. So we define a CPA oracle that wraps around these PRF oracles B has access to, and uses them, right? So we're going to use the PRF oracle B has access to in order to implement the CPA oracle that B exposes to A in order to run it. So here's literally the entire definition. It's quite simple. So how do we answer encryption queries that the adversary might want to make? Well, we'll use our PRF oracle to compute the mask on nonces, given the nonce as input. And then given that mask, we'll just XOR it onto the plaintext and return that as the ciphertext that we give back to the adversary. So now it should be pretty clear that if this O.F is actually the pseudo-random function, the concrete pseudo-random function, with the key K that's sampled at random at the beginning of the world, so at the initialization of this, of the CPA experiment, then this ciphertext we produce is going to be exactly the real ciphertext that the real encryption oracle is going to produce. On the other hand, if O is the random function, then O.F is going to be the result of that random function. And then what we produce as output here is going to be exactly the result of this modified enc applied to the truly random function. So we'll have this correspondence. And then so then the only thing that we do, so once we've defined this CPA oracle, we can just run A with the CPA oracle as part of the CPA experiment, and that's just going to be the whole of the reduction B itself. And then we need to see the proof, but I think I have run out of time as part of the lecture. So I'm not sure how to handle this, because it's important that we see some examples of that, so you have something to go on when you start the exercises.
I think it's perfectly fine if you go a bit longer. I mean, we had a break, right?
Yeah, I guess you did.
So. I
didn't, because I was panicking, but
yeah. I mean, if you want, you can also take a 5-minute break and then continue.
I don't need it. I think that did give me a kick. So I'll carry on. Go as far as I can, and then when you think you've had enough, you just let me know, and we move on to exercises and quick discussions. Other questions so far, though? No? Okay. So again, what we want to do now, we've got this concrete adversary B. I did mention something about complexity and about number of queries. So let's just quickly go over that argument, that bit of the argument, so we don't have to come to it again later on. So what we want to say about B, about this adversary B, is that it is as efficient as the adversary A, just so that we're sure that B doesn't just implement a brute force search, and that it makes the same number of queries so that we can somehow concretely relate the actual advantage of A breaking the encryption scheme and the concrete advantage of B breaking the PRF, or distinguishing the PRF from a random function. So here we've got an efficiency argument. So what is B actually doing in its code? Well, it's running the CPA experiment. So it samples a key, essentially, for the CPA oracle. Well, it doesn't even, right? That's part of the PRF experiment that's happening. And then it runs A and just return A with these oracles, or CPA, and then return the result of that. And each time A makes a query to its encryption oracle, what B does is make a query to its PRF oracle, and exactly one query to its PRF oracle. So it makes exactly the same number of queries. And then it computes an XOR, which is almost free, right? So the complexity of B is almost exactly that of A. The only cost is one XOR per query the adversary A makes to its CPA oracle. So we've got that dealt with. B is as efficient as A, and it makes the same number of queries. And now the only thing we need to prove is that its advantage, the advantage of B in distinguishing the PRF from truly random function, is exactly the advantage of A in distinguishing a concrete encryption scheme from one that's ideal and just produces random ciphertext. So we do that by essentially proving the steps as described on the left in the slides. But in EasyCrypt, it's a bit more verbose than just waving our hands and saying those things are the same. So the proofs that we do in EasyCrypt, they're often wrapped inside a section like this. And what that section does, it allows us to do several things. One, it allows us to quantify over modules that we want to keep abstract. So here we only have the adversary, but in certain settings, you might actually want also some of your building blocks to remain abstract. And so you could quantify over them in this way as well. And the second thing is it allows us to hide some details of the proof that we don't want to appear in the actual result in the end. So if you've got lots of intermediate games or lots of things going on inside your proof, you might want to hide those. That's not the case here, but the section mechanism can be used for that. And I'm not exactly sure if the Jasmine part of the proof will make use of it. So we start a section that we call proof, and then we declare a module A. So we just say, well, whatever we're proving now is going to be parameterized or to be true for all possible adversary A, for all possible modules A that have the type adv_cpa that we defined earlier. So again, adv_cpa is any algorithm that's called main that takes no inputs, has oracle access to one of those CPA oracles, and produces a Boolean. In addition, you see that in that quantification, we've got a bunch of things here that are happening, and those are memory restrictions. So we're saying that adversary A, it can do almost anything it wants. There's one thing it cannot do, and it is access the memory, the global variables of these modules that we specify here. So it cannot go and look inside the state of the real scheme. And the real scheme is, again, that wrapper that actually holds the secret key. So if the adversary could go and look at that secret key, obviously it could distinguish between the real and the ideal setting. The adversary cannot look at the real PRF either. And again, this real PRF is the experiment where the key is actually stored in a global variable. So we really don't want the adversary to look at that either. It cannot look inside the state of the random function, and the random function, if you recall its state, actually has the map that's being maintained. So again, the adversary could look that up if it could access that variable and distinguish just based on looking up the value before making a query, for example. It cannot look inside this wrapper, which has the list of nonces that have been used. And this one is more technical. And same thing, it cannot look inside the count module, which is one that we use to count the number of queries the adversary makes to the PRF. So these are more technical. Why the adversary can't look at them, it's more that that there's parts of the proof that are tedious if we allow the adversary to look at them more than anything else. So we just have them float around and be there. Now we're getting into the part of the logic that you'll be making the most use of in today's lessons, and that's PRHL. So here we've got lemmas that we want to prove, and let me just show one of them. We want to show that two games or two programs are actually equivalent. And we want to show that for all adversary, but we've already quantified over the adversary. So we want to say, well, this game with this adversary is equivalent to that game with the adversary B applied to it. So with the adversary B that we just saw. We want to show that basically the only thing we care about is that the probability of returning true in one is equal to the probability of returning true in the other. We just prove that at one level up. We'll just say they are the same program. And that's what this equiv is saying with this pre and post condition. So here, what this lemma is saying is that we've got an equivalence between two programs, and that equivalence is going to be parameterized by a precondition, which is a relation between the two initial states, and a postcondition, which is a relation between the two final states, so the two states at the end of the execution. And we're going to say, so if we run this program, so the CPA experiment applied to the adversary A and the real scheme, and we run in one memory, so which I will call the left memory in the rest, and we run this program, which is the PRF experiment applied to B of A and to the real PRF in two initial memories. So the left and the right memory are such that they agree on the state of the adversary. So the adversary has the same state on both sides. And that's so that it behaves in the same way. Essentially, the only thing we want is that the adversary starts in a state on both sides where it's going to be behaving in the same way. Then if we know that those two programs start in one of those pairs of states that agree on the globals of the adversary, on the global variables of the adversary, then those two executions will either both diverge or both terminate in a state where they will agree on their result, which is this res variable is the result of the program. So whatever is in this return statement right here, or in the code in EasyCrypt. And so here that will be the adversary's output, essentially. So again, what we're saying here is if you take those two programs and you run them in any two memories that agree on the adversary state, they will, let's ignore the fact, the case where they both diverge, but they will both terminate and with the same exact value, with the same output. And we're going to prove that general. So when we prove that, and now I'm going to go full screen and try to get this back out. So we enter into this proof mode for EasyCrypt, which I could have showed earlier, except I skipped over a bunch of stuff. So I'm going to enlarge these so that we can see what's going on. So we're now entering into this proof state where we've got a program, so a proof goal that has a program, or a pair of programs in this case, a precondition and a postcondition. So it's asking us, please prove this equivalence, which is exactly just a representation of the goal we just stated we wanted to prove up here. And we're going to start proving things about it. And the idea of the relation of whole logic that we're in, so probabilistic relation of whole logic, PRHL, is that we're going to prove the programs are equivalent by showing that at each step of the program, starting from the end, they actually yield the same results given the same inputs. So the first thing we do is usually called proc to actually say, in order to prove this fact about these two experiments, about these two programs, we're just going to prove the facts by looking at the code of the programs. There are various things we can use to prove those such facts without looking at the code. But in this case, we want to actually go ahead and look at the code. So here, all it's done is replace the left-hand side program with the code of the left-hand side program, and replace the right-hand side program with the code of the right-hand side program. And then the result is actually replaced with the expression that was in the return statement for those programs. So in this case, it's the same value b, the same variable b. In this case, it's simple enough, so we can just inline everything. And here, again, all it does is replace the code for procedures that we have the code for with the, it replaces a call to procedures that we have the code for with their actual code, and does a bit of transformation to avoid variable clashes and things like this. So here we've got a B0, for example, as the output, just so that we can then store the result in B as well. And now we can already see that there's a bit more correspondence between the structure, right? So here, the main issue we had is we have one adversary A on the left, which is completely abstract. And on the right, we've got a call to B, which is something we've built, right? So what we want to do is demonstrate that reach a point where we're reasoning about the same adversary on both sides. And I'll be starting to do a bit of hand waving. So I think if you can't see the camera, now is a good point to get that up as well. So, and again, so we're looking at from the end of the program, we want to really bring it to a point where we see the correspondence between the various steps of the program. So here we've got a bit of trailing stuff. One very useful tactic in EasyCrypt is WP, which computes the weakest precondition. And that's a very useful thing. So here you've got a postcondition that we want to prove, and that's an equality between two variables, one on the left and one on the right. So the value of B at the end of the left program should be equal to the value of B at the end of the right program. Now, the value of B at the end of the right program, if this, so we can see from this line of code, is going to be equal to the value of B0 at the end of line 4. And WP kind of computes that for us by going through the programs backwards and as far as it can. So here it will stop quite quickly because we've got an abstract procedure that WP doesn't know anything about. But we can see WP here will consume this last line and actually reflect the effect of that line on the state in the postcondition. So before we had to prove that the value of B on the left was equal to the value of B on the right. And now we've taken into account the fact that the value of B at the end of the execution on the right is exactly the value of B0 at the end of line 4 on the right, and reflected that in the postcondition. And so now we've got these tags, B in memory 1 and B0 in memory 2. And this tag 1 is going to be the left memory, this tag 2 is going to be the right memory, and curly braces are going to be used to tag with a memory. And there's a couple of places where those might pop up. So we can chain all of these things together and get to this point. Now, the problem we have now is that we're reasoning about the adversary call. And the adversary, we know nothing about it, apart from the fact that it's the same on both sides. So it's the same adversary that's running on both sides. And we also know that it starts from the same state, right? The state of the adversary at the start is going to be the same. So what we need to do is show that the adversary starts from the same state. And so the distribution of the first oracle query is going to be the same. The adversary is going to be essentially making the same, from our point of view, is going to be making the same query to its oracle on the first query. And as long as we make sure that when we answer that first query, we answer it with the same value, or with the same distribution on values, then we know that the adversary state on both sides, when that output value comes back, is going to be the same again. And so the adversary is going to make the same second query to its oracle, and so on and so forth. And to reflect, so you don't have to do that reasoning. EasyCrypt does it for you. So we've got this core rule that's been proved to be sound and to correctly reflect equivalences between adversary calls. And that's going to be parameterized with an invariant. There's going to be an invariant on the state of the oracle. So again, a relation on the states of the oracles on the left and on the right. That's going to guarantee that given the same input, the oracles are going to return the same outputs and preserve that invariant on their state. So this state is a bit of a magical bit that I don't think you'll need to come up with in the exercise. So in this case, we're going to say, all right, I'm going to apply that rule that says, as long as you can show to me that the oracles will return, the oracles that the adversary can call will return the same output given the same input, and that the invariant you're giving me is preserved, then I will show to you that these two adversaries return the same output given the same inputs. So, and this invariant in this case is that the nonces that are used on both sides are going to be equal. And again, they're initially empty, and those nonces are exactly the nonces that the adversary gives to us. So as long as we make sure that the adversary always gives us the same inputs, those nonces will be the same on both sides. The keys on the real scheme side and the real PRF side are need to be the same so that we can say the encryptions happen in the same way on both sides. But we know that they're going to be the same, or at least follow the same distribution, because we're sampling them in exactly the same distribution right here, right? So here we sample K and we store that in the real scheme. And here we sample real PRF.K, so directly the PRF key, directly in the same distribution D key as well. So we know that this is initially true, and then the oracles never override that. So this is really an invariant that we rely on, that we never need to prove again. And then we also need to know that the size of the nonces, so the number of queries on the left and the number of queries the PRF adversary makes on the right are the same, and that's because we're actively enforcing the fact that the adversary doesn't make more than 2 queries on either side. So we've got the behavior of the oracles depends on the number of queries the adversary has made, and so we need to explicitly have that invariant. So let's just run through it, see what it's telling us. So when you step through, sorry, I should probably mention that. You can step through each of those tactics, as we call them, using this next button, or you can use Control-C, Control-N to step forward one step, or yeah, one step. So when we use this call tactic, you'll see up here that we've got 2 goals that remain. The first one is exactly the one I was talking about on the oracle itself, right? So the adversary, we know that its type is @CPA, so it's specified up here to be a CPA adversary. And so we know that it has access to an oracle that is one of these ANK oracles. And we know exactly which one that is because we've got a specification right here of which oracle is given to the adversary on the left and to the adversary on the right, right? So we can specify that. And so here, what we're asked to prove is assume under the assumption that the adversary provides the same inputs and that the invariant we've provided to the call tactic actually holds initially. Prove to me that when you run these oracles, so the oracle that's provided to the left adversary and the oracle that's provided to the right adversary in those initial memories that are related by this, then we'll end in a final state that agree on the result, so that give out the same result back to the adversary, and such that the invariant still holds. So we need to maintain the invariant under the assumption that the adversary gives us the same inputs. We need to maintain the invariant and make sure that we give out the same outputs. And from then on, EasyCrypt and the logic take care of the rest and show that the adversary therefore executes in exactly the same way on both sides. How do we prove this result? Well, we can prove it. Again, this is just a sub-goal, but that's an equivalence by itself, right? So we can, again, say, okay, we'll look at the code of it. And here we can see already that there's quite a few things in common that agree on both sides. So again, we need to prove equivalence, and we'll get that essentially for free on those first bits. But here again, internally, we've got a small difference where on the left, we've just got the real scheme oracle. On the right, we've got this reduced oracle, the oracle that the reduction implements using the PRF. And so we can highlight those differences here by doing an inline star, and we'll see that there's really something going on at this stage, right? But importantly, most of, like all of those things, in this case, it's a simple example, but they're actually all deterministic. There's nothing probabilistic that happens. So we don't sample, we're not using any abstract operators or anything like this. And so EasyCrypt is really easily able to deal with it with auto. And I think most of the cases that you'll be looking at will be looking at auto as well. So again, keep in mind what we need to prove. We need to prove that given the same inputs and states that are related by this invariant here, when we execute the program on the left and the program on the right, we'll get the same outputs and the invariant is still preserved. Now, what are the differences? On the right, we check, because we're calling the PRF, we check that we're not calling it more than 2 times. And again, this is because we chose to actively enforce those restrictions. And then in order to compute the output, we'll be using F applied to the real PRF.k, and then producing the result as the result XOR P0, XOR the P essentially. On the left, we'll be using F applied to K and N1, and then XORing the result to P1, to the plain text. But then K is real scheme.k, right? And we had this invariant that real scheme.k in the left memory is the same as the real PRF.k in the right memory. So we'll be able to prove that equivalence. And then for dealing with this count, we know that because we're inside this if statement here, we know that the size of wo.nonces is less than q. And we also know from our invariance that the size of this wo.nonces is equal to counters. And so we'll be able to say, well, if we went through this, we'll definitely go through this as well. And we don't need to do that manually. We can tell EasyCrypt, okay, simplify as much as you can. So auto gets rid of the program, and then this crush symbol here does a bunch of simplifications on the goal and gives us only what it could not deal with. And the only thing it could not deal with was literally prove that that we're going to go into that then branch on the count on this if statement that I was just pointing out. So in this case, EasyCrypt is asking us, please prove that we are going to go into this case. Actually, it's not even doing that. It's asking us, please prove that count.c plus 1 is actually equal to the size of wo.nonces after we've added the nonce we have in it. So this is the only thing that EasyCrypt could not deal with on its own. And in this case, it's just a simple commutativity of addition. And so SMT deals with it. So EasyCrypt has these layers of logic. And then in the end, at the bottom, we can actually call SMT solvers, so satisfiability modular theory, that are automated theorem provers that do really well at reasoning about program constructions, essentially. And so we have a shortcut to call them, which is the / hashtag or /sharp, which allows us to call SMT in simple context as well. And so now we've proved that those oracles always produce the same result given the same inputs and equivalent states, where this equivalence is given by this invariant we specified. And we only have to prove, so this is a big postcondition, but the only thing we have to prove now is that this initialization code that we had essentially brings us to a state where we call the adversary with the same state on both sides, and the invariant that we relied on to do the rest of the proof actually holds. So this is asking us to prove to me that the adversary's inputs are equal. That's this. There's no inputs, so that's always true. Prove to me that the adversary's global variables, the adversary's state, is the same on both sides. And prove to me that the invariant you told me you're going to rely on is actually true initially. And because then we also prove that we maintain that invariant through the execution, we can bootstrap essentially the induction or the iterative reasoning based on this. The rest of this post condition is essentially telling us, prove to me that the fact that the adversary's output is the same is sufficient to prove that the experiment's output is the same as well. But the experiment's output is actually, so we need to prove this. If you parse all of this, you'll see that this implication essentially means we only have to prove that the results are the same, but we actually have it as an assumption right here. So it's saying for all possible outputs that the adversary produces, such that the condition you placed on the output of the adversary, which is that those outputs are equal on both sides, implies that the post condition you had to prove, which was that the adversary's outputs were the same, holds. And so we can trivially solve that. And again, the invariant, the fact that it holds initially, is going to come from the initialization that we have. So the fact that the keys are equally distributed, well, they're sampled in the same distribution. The fact that wo.nonces is the same on both sides is coming from the fact that we initialize it to empty on both sides. And the fact that the size of that empty list is equal to count.c is coming from the fact that on the right, we initialize count.c with 0. So again, we simplify a lot of things that way. So this was the first introduction to equiv. And I know I went quickly, and I know it's not actually the hard one, but it should give you a nice example of what's going on the simple equivalence. Based on that equivalence, we can actually prove the probability statement or the probability equality we wanted. So if you recall, what we actually wanted to prove is not some generic equivalence between two programs. It was the fact that two probabilities were actually the same. So the probability of the CPA experiment, A making the CPA experiment, the real CPA experiment return true, was the same as the probability that B makes the real PRF experiment return true. And we can actually express that exactly, almost exactly as specified here in EasyCrypt. The only difference is that we need to specify an initial memory from which the execution starts. And in this case, it's often simpler to assume that we start from the same memory on both sides, although the only thing we really need is that the globals of the adversary are the same on both sides. So here we're just saying, for all possible initial memory, as long as it's the same on both sides, if you run the CPA experiment with A and the real scheme on the left, if you run the CPA experiment with A and the real scheme in that initial memory, it returns true with the same probability as the PRF experiment running with B of A and the real PRF running in the same initial memory. And this is just a consequence by definition of this equiv statement, of this logical statement here of this equiv. This equality of probabilities follows. So by equiv with the name of a lemma is going to tell us, okay, I've got this equivalence between these two programs. This is exactly what you need to prove this equality of probabilities. There's a lot more going on in the background. So there's actually some checks that the precondition that's on the equiv actually holds. And in this case, it holds because it's the same memory on both sides. So the globals of the adversary are obviously equivalent because it's, again, the same memory. So we can kill that. And the second condition that we have to prove is that the post condition of this equiv is sufficient to prove that the two events whose probability we're measuring, so here, the fact that the experiment returns true and the fact that the experiment returns true, are equivalent. And here we can actually generalize, well, we can illustrate, so we could prove an inequality here and we'll see that here we need an implication in this direction, for example, to prove that a particular probability is less than another probability. We just need to show that the event on the left is it implies the event on the right. So it's smaller than the event on the right. So we can manipulate, essentially prove equality of probabilities or more generally inequalities of probabilities just by reasoning about equivalences of programs. So proving that two programs behave in the same way or in ways that imply that in related ways, essentially. Let's put it simply as related ways. I want to stop now. There is this more complex proof where we actually build in reasoning about the one-time pad. And I think we'll discuss it when you get to it in the proof. There's slightly more work to be done to actually show that that things line up and that when you sample in one way on one side. So here, what we need to prove is that this this oracle essentially samples in the same distribution overall as just sampling ciphertext at random. And for that, we need to come up to produce a slightly more complex argument that says, well, if you sample in two distributions that are related by a bijection that preserves the weights, then you're essentially sampling into distributions that can't be distinguished by an adversary. And so that we build in a bit more work in there. And the invariant needs to be adapted because we're talking about the ideal functionalities in that case. So we're no longer talking about keys being equal on both sides, but we're talking about maps holding the same values on both sides. So in the modified enc, we have a map from nonces to plaintext. In the ideal enc on that side, we've got a map. Sorry, we on the PRF side, so not displayed here, we've got a map from plaintexts to ciphertext. Sorry, from nonces to ciphertexts, which is exactly the same thing. I think that's it. So I want to stop here. We'll give you the exercises after a quick break. And I'm happy to take questions now that may have arisen during this first half of the lecture and move on from that. Are there questions that I've missed?
So first of all, thanks a lot, François,
Welcome.
for the talk. I think there were no questions so far in the chat.
Okay.
I guess right now the group is still somewhat small. I guess many people will just planning to watch the video like afterwards and forgot that there's an instruction. People are used to this format too much now. There's actually a question.
So what theory and SMT solvers can you use? So EasyCrypt connects to SMT solvers through Y3. So we essentially support all SMT solvers that Y3 actually supports. By default, we try to target Z3 because it's American, Altargo, and CVC4. And typically we actually, our proofs usually, well, in the standard library, we actually try to make sure that the proofs work with any single one of them, although that doesn't always work. But you can just use any SMT solver that's supported by Y3. And that's a lot larger set than that. And Y3 also supports solvers that are not SMT, so that are thousands of problems for theorem provers, for example, so TP-TP solvers, they are supported. And you can also just extract to interactive theorem provers like the Coq theorem prover and other tools that you have. Although I don't know why you would want to do that because we've got a full-fledged proof assistant here. Although it doesn't have all the libraries you might want. To have if you're doing deep mathematical reasoning, but it does have quite a lot of them. So, sorry. Going back to the theories, so we've got core theories that are essentially just those provided by SMT that we connect to, and then we've got a lot of advanced theories built on top. So we've got lists that are not supported by SMT, but are really useful in a lot of things. We've got sets, we've got a lot of things that are built and are often used in specifying cryptography, and especially in managing those restrictions that are placed on the adversary, and that are not typically supported by SMT. And those are usually not handled very well by SMT. So we do have some interactive proofs going on when you've got more abstract construction happening as well. There is a question about eCall. Yes, there is an undocumented tactic eCall that we use in the proof. It is essentially saying, well, instead of trying to come up with an invariant that captures the behavior of this call, of this procedure that we're calling, we actually are going to say, well, this procedure is equivalent to some operator that we've defined somewhere else, and that's what eCall is doing. So it's saying, well, okay, you want to deal with this procedure call. I'm going to just you want to deal with this procedure call. I'm going to say this procedure call, its semantics or its behavior is exactly captured by this operator that is specified as a parameter. And then it's going to generate a proof goal that says, okay, prove to me that that is true. And then in your post condition, you will just get the fact that the output is equal to the operator applied to the input. So it's really a simple replacement with an operator kind of tactic. As far as I know, this is the only way I've seen it used. It could be more powerful, but Benjamin will let us know if it is.
Yes, maybe you can do some correction on that part. So it's rather technical, but it's more than sometime when you, like in a correct deck lemma, your lemma is parameterized by some value. So the K and the K, N, and C here. And when you do the equal, it's allow you to provide directly the value of K, N, and C. Okay, so it will allow you to specify this value just by the one you want to use just before the call. So here you say, I want to apply this lemma with the value underscore K, underscore N, and C.
Okay, so that was me completely wrong. So what you may have seen I don't know if you've used EasyCrypt a lot. What you may have seen before is things like exist star. Wait, no, we have those floating around already. So you may have seen things where you've got exist star and then a couple of additional things where you want to extract values from the memory and then provide them as input to the call. And here, I guess that's doing a similar thing.
Yes, exactly.
Cool. So yeah, there's a variety of tactics. Some of them are not documented, and we should really not be using them in here. But there is a cheat sheet somewhere in the material. I'm not sure if a link was provided while I was gone, or if not. But anyway, so there's a lot of material coming your way for the exercise session. I think we should drop the link in. So you don't need to have EasyCrypt running on your side, because we'll also be providing a link to virtual machines that you can access from your browser, and to a list of users and usernames and passwords that we'll ask you to be respectful about, I guess, because we're literally just giving you a list of usernames and passwords. And I think then we can quickly get started with the exercises.